this a little bit. That's about the best that's gonna get. So, that was the last module with me. Analyzers and monitors. Oh, I forgot about this. I don't know that I'll show every single one of these. Whoever wrote this module kind of sucks. They put 15 PowerPoint slides, so if I don't get all the pictures, they're just gonna be pictures. But I'll go through as much as they want. All right, trade terms. They're gonna have a ton of different trade terms, like for chemistry and stuff like that. Because whenever they're talking about analyzers and monitors, usually you have some type of mix-up or mixture of acid or a base or something to clean your not your equipment, but whatever your product is, stuff like that. So all these would be worth going through, but this is pretty much like high school chemistry class trade terms. I do have the parts per million highlighted as an online test question. So parts per million is the concentration of solution, expresses the parts of solute per million parts of solution. Y'all heard of a ppm anywhere recently? Watch the saltwater intrusion stuff. So the big thing is that we don't get the 250 ppm of salt water, so parts per million in our water and stuff like that. You'll hear that St. Bernard is no longer affected. Came out with that today. So at least that's what the Corps does not expect us to get too high of a salt level. So they have, that's the 250 parts per million is the cutoff where it's unsafe to drink. They say like our drinking water might still taste a little salty or something like that, but it's not to the point where it's like an dehydrate us to drink it. But that's like whenever they make a mixture of something, like that's what they're looking for like parts per million of different parts of the solute in the solution. I think most of the other stuff, like you're gonna know just from high school or reading through this stuff. I'm not gonna read through all those. pH is gonna be important. pH is gonna be a big one. That's gonna be the small. Actually, there's another lab that we're gonna do all together, which is it's kind of just showing you how to use a pH analyzer. And I pull out like coffee and orange juice and vinegar and bleach and stuff like that, and have y'all kind of guess what you think the pH is gonna be, and then we'll analyze it and see what it actually is. So that's something we'll probably do maybe next Thursday or something like that, just to knock it out. Page 2, the science of matter. So again, just at least section 1 is kind of like a review on chemistry. 110, I've got the third sentence with the highlighted word atom in it. The smallest particle of matter with a distinct chemical identity is the atom. The immediate next sentence is also highlighted. Atoms contain up to 3 different particle types: proton, neutron, and electron. So the flow of electrons is called what? far as electricity is based. Current. Okay. The flow of electrons is current. So usually, like this outer shell is called your valence shell, and that's where the kind of loose electrons lie, and like from atom to atom, the electrons move, and that's essentially how current flows. Copper is a good conductor because it has a valence shell that's able to share with other atoms and stuff like that. So that makes it a good conductor. Elements 111. Right hand side of the page, I've got the sentence that has atomic number and the sentence after it highlighted. Since each type of atom has a unique number of protons, elements are identified by a numeric value called the atomic number. The atomic number corresponds to the number of protons in the nucleus of an atom. Next paragraph, first sentence is highlighted. An element's atomic mass, also called its atomic weight, is an average based on the masses of different isotopes of the element. Periodic table. So I got the periodic table. You guys have probably seen before on page 3. They just want to talk about like how, like columns. Remember, columns are vertical. So you have columns 1 through 18, and then you have the different rows. So like row 1, 2, 3, 4, and they're spaced together. Like the columns are going to be like elements with each other. Like these are like column 18 is column 18 is the noble gases. Does that sound right?
I think so.
I think I might have it. Page 4. Oh, that's what I messed up. The horizontal rows, like the rows are called periods. Not rows, they're called periods. Yep. The last sentence of the first paragraph on page 4 is highlighted. Each period in the table ends with a very unreactive gaseous element called a noble gas. So column 18 is a column of noble gases. The last paragraph before 113, the whole thing is highlighted. The elements within a given group behave in similar ways chemically. For example, sodium and potassium are very much alike. That's why potassium chloride can be used for people with high blood pressure as a replacement for sodium chloride or table salt. It tastes and behaves similarly, but it contains no sodium. 113, compounds. Okay, I guess I messed it up. So the horizontal, the rows are called periods, and the columns are called groups. So rows are periods, columns are groups. Compounds, first sentence of compounds is highlighted. Elements combined together to form substances known as chemical compounds. It's the first sentence of 113. Out to the side of that, I wrote example H2O, which is water. Water is a compound. 120, chemical reactions. First sentence of 120 is highlighted. A chemical reaction centers upon the atom's outermost electron shell, known as its valence shell. The first sentence of 120. Chemicals reaction centers upon the atom's outermost electron shell, known as the valence shell. So that's this one out here, valence shell. Chemical reactions, 120. First sentence I already got that one. The last sentence of that paragraph is also highlighted. When atoms react, they tend to gain, lose, or share electrons with other atoms in order to complete their valence shells. Chemical bonding, 1-2-1. The big thing out of this is you're going to need to know what the difference between an ionic bond and a covalent bond is. So my first highlight is the first two sentences of the second paragraph in 1-2-1. When a metallic atom reacts with a non-metallic atom, an electron gets transferred from one atom to the other. The process links the atoms together in what is called an ionic bond and forms an ionic compound. So ionic bond happens when a non-metallic atom combines with a metallic atom. Covalent bonds at the bottom, the first two sentences of that last paragraph are highlighted. When two non-metallic atoms react, they share electrons between themselves, essentially passing them back and forth. This process forms a covalent bond. Page 7. Still talking about bonds. That last paragraph before 1-2-2, first two sentences are highlighted. Finally, metal atoms can form bonds with each other in which their valence electrons get shared among a huge number of atoms and form a kind of electron sea. This type of bond is called a metallic bond. That's, if I remember right, that's usually the questions that people struggle with on this test is the difference between the ionic, covalent, and metallic bonds. 1-2-2. Atomic mass and chemical reactions. Online test question, all the way in the top right of the page, the first three sentences in the top right. A mole consists of 6.02 times 10 to the 23rd particles. This may be atoms, formula units, or molecules. 1 mole of any element has a mass in grams equal to that element's atomic mass value. Now, some of this stuff, like, it's good to know, but I don't feel like it serves us any purpose as far as like instrumentation or. I'm not going to get into it too much. Page 8, concentration. Concentration. I've got the sentence that has parts molarity and parts per million highlighted. You'll have two separate questions that come out of that one sentence. Two terms commonly used to describe the concentration of a solution are molarity and parts per million. You'll need to know how to find the molarity of a solution. So if you look at step 3, they talk about finding the molarity of a solution. All I have highlighted is molarity equals the moles of the solute over liters of solution. I think they give you both in the question, and they just ask you to find the molarity. So you just divide the moles of solute by the amount of liquid, or the liters of the solution. Acids, bases, and pH, 141. Ions, 141. I've got the second sentence highlighted. A charged particle is called an ion. Charged particle is called an ion. Acids and bases, 142. Third paragraph in 142 on page 9, the first 5 sentences are highlighted. An acid is classified as strong if it ionizes into a lot of hydrogen ions that form hydronium ions when added to water. For example, hydrochloric acid ionizes essentially 100%. Consequently, it's a strong acid. Acetic acid, found in vinegar, does not ionize completely. Only a small percentage of its hydrogen turns into free hydrogen ions. Consequently, it's a weak acid. Y'all remember what's pH neutral on the scale? So 7 is pH neutral. And then if you're going more acidic, you're going towards 0. If you're going more basic, going towards 14. So hydrochloric acid would be more like I think like a 2 or 3. I don't know what the other acid would be. This is definitely safe. But the thing to note is that whenever you're going down the scale, I can't remember if we've talked about this before, who I've talked about this with, but it's this important note down at the bottom. The pH scale is logarithmic, so it's not linear. Each unit represents a factor of 10 change. For example, a pH of 9 is 10 times as basic as a pH of 8. So it's not like an increasing step as you go. It's like 7 is neutral, then 6, then 5, and then 4 is way up there. Like a pH of 3 is 10 times as acidic as a pH of 4. And same thing on the other side. A caustic number of 11 is 10 times more than 10, right? So it's not linear, it's logarithmic. pH 143, first sentence in 143 is highlighted. Convenient way to state the acidity or basicity, alkalinity of the solution is the pH scale. Skip a sentence, and I got the third sentence highlighted. As the quality of the hydrogen ions increase, the solution becomes more acidic. As the quantity, I guess it's quality, as the quantity of hydrogen ions increases. And then next paragraph, first sentence is highlighted. pH scale typically ranges from 0 to 14. So you need to know that less than 7 is acidic, and more than 7 is basic. 144, neutralization of salts. Last sentence of the first paragraph. Salts are electrolytes, as are acids and bases. Salts are electrolytes, as are acids and bases. Take a couple minutes and see if you can find those 7 questions on page 11. Run through those. Number one, smallest particle with a distinct chemical identity. Atom. 2, the atomic number of an element indicates.
B.
Protons in the nucleus. B. 3, in the periodic table, elements with similar chemical properties are found where?
A.
Same group. A. 4, chemical reactions always involve the electrons in the valence shell. 5, a chemical bond in which atoms share electrons is called a B covalent bond. 6, technician mixes 5 moles of solution of 5 moles of sodium hydroxide with water to make 3-liter solution. What is the molarity of the resulting solution? 1.7. Okay, I'll go with that. I mean, I'll take 5, divide by 3, you get 1.67. And 7, an acid that ionizes to only 5% of its total hydrogen atoms when mixed with water is classified as weak. If it doesn't ionize almost to 100 or something like that, the less it ionizes, the weaker it is. Section 2. Analyzing physical properties. I don't know, density and turbidity are important. Specific gravity, somewhat, as far as we're concerned. I don't know. 210, density and specific gravity. You're gonna need to know the equation for both. So I've got density equals mass over volume highlighted, and then down below the next 2 paragraphs, specific gravity equals the mass of a specific volume of a substance over the mass of the same volume, volume of water or air. You're gonna have 5 questions come off of those 2 highlights, so it's gonna be that'll be an important one. Hydrometer. First sentence, the hydrometer is highlighted. One way of measuring a liquid's specific gravity is with a device called a hydrometer. Air bubble measurement. 212. First sentence is highlighted in 212. The simplest and perhaps most widely used method of measuring density and specific gravity in processes is using bubble tubes and a reference chamber in conjunction with the differential pressure chamber, the pressure transmitter. Displacement measurement. 213, first sentence is an online test question. A displacer is sometimes mistakenly called a float. Two 214, densometer. First 4 sentences are highlighted in 214. Measuring the density of gases is important in the gas transmission of petrochemical industries. This measurement can be accomplished using a densometer with a probe. The probe includes a vane that is installed in the pipeline that contains the flowing process fluid. The vane oscillates in the fluid, causing an acceleration of flowing process fluid. Page 14 and 15. Viscosity. On page 14, second paragraph, first 2 sentences are highlighted. Of all the physical conditions, temperature has the greatest effect on viscosity. As the increase in temperature causes a greater separation among the liquid molecules, a reduction in shear stress, and therefore a decrease in viscosity. So think of it like motor oil. Cold motor oil is pretty thick and viscous. But after it's run in your truck or car for a while, you take the cap off, it's gonna flow pretty freely out of there. It's not gonna be as thick and stuff like that. So as you raise the temperature of something, you lower the viscosity of it, usually. Viscosimeters, 221. First sentence of 221 on page 15 is highlighted. Viscosimeters are instruments used for measuring the viscosity and flow properties of fluids at ambient or other specified temperatures. The first sentence after the bullet points is highlighted. A falling ball viscosimeter measures viscosity by measuring the time required for a ball to fall through a specific distance of liquid under test. So if you have up here on the board, you have a distance amount, you let the ball go, however long it takes to get to the bottom, it can determine the viscosity based on that. Page 16. Turbidity. 230, first sentence is highlighted. The cloudiness of a fluid caused by a suspended particle is known as turbidity. So you'll have different types of analyzers to measure turbidity, measure the cloudiness of a fluid. Nothing 231. 232, I have the whole first paragraph highlighted on page 17. In 232. The transmission turbidity analyzer contains a light source, lens, sample cell, photocell, and a control unit with a readout. So this is the picture of what's on the bottom of the page. Which I'm assuming that I don't have a picture of. Or this that's up on the board. So you've got light source, lens, sample cell, photocell, and control unit with a readout. The lens focuses light from the source through the sample cell, where it's measured by the photocell. Liquids with low turbidity absorb and reflect very little of the light, so the photocell's output is high. Liquids with high turbidity absorb and reflect a significant portion of the light, so a photocell's output is low. The control device amplifies and transmits the photocell's output signal to the readout device. Out to the side of that, pretty much what you need to know is it uses light to measure turbidity. It uses light to measure turbidity. Page 18 and 19. And a couple more analyzers. They have the reflection analyzer, and then the ratio analyzer. I don't have anything on 18, but page 19, I've got first only two sentences. First two sentences of 234 highlighted. A ratio turbidity analyzer uses a more complex system to measure turbidity. Sharing technology from both the transmission type and the reflection type analyzers. See figure 22, in which light from a common source passes through a rotating chopper disc that alternately blanks out one light beam at a time. Key in on the rotating chopper disc. You need to know that the rotating chopper disc is what's used in the ratio analyzer. So that's this part. Rotating chopper disc. See if you can answer those 5 questions on page 20. Right, those. Number one, a block of wood, 6 centimeters on each side, has a mass of 160 grams. What's its density?
27.
It's A. So density. That's not how to spell it. Equals mass over volume. So it gives you the mass is the whatever the grams are. So it's got you got 160 over your volume. So how do you find the volume of a cube? Length times width times height. So they're saying it's 6 centimeters on every side. So it'd be 6 cubed. So you'd have to do 6 times 6 times 6, which is 36 times 6, which should give you what? 2160. So you got
260.
260. That's not 2160. 260. So 160 divided by 260 is 0.74 grams per centimeter cubed. Go with that. Number 2, crude oil has a specific gravity of 0.92. 1 gallon of water has a mass of 8.3 at room temperature. What's the mass of 1 gallon of crude oil at the same temperature?
B.
It is B. So working through this one, a different color. So our equation is specific gravity. Gravity is equal to our mass of specific volume of substance. Mass of over, that's a lot. Over the mass of the same volume of water.
No transportation, no cars. Yeah, they told me this Saints game tonight. There's like.
Oh yeah, it's busy tonight, isn't it? Gosh, not bad. Goes in and out. So if I've got mass of a specific gravity of a substance over the mass of the same volume of water, it gave me the specific gravity of 0.92 of the solution, and then they also gave me the mass of the water. So the mass H2O is 8.3. So I plug those into my equation, and I get 0.92 or 97? 92, right? 0.92 is equal to, I'm just gonna call it X, that's what we're looking for, over 8.3. So how do we get X by itself? Multiply both sides by 8.3, so I multiply that by 8.3, cancels out. 0.92 times 8.3 should give us our answer, X equals 7.6 pounds. Number 3, we're on page 20, the last chapter. Number 3, the instrument that works together with differential pressure transmitter to measure density. Find that one?
No bubble.
Couldn't find that one?
Bubble.
Bubble. Oh yeah, sorry. 3 is C. Number 4, what class of instrumentation measures a fluid's resistance to flow? A, the viscometer. 5, the measure of cloudiness of a liquid is called its turbidity. C. Section 3, analyzing chemical properties. Flashpoint is, I've got flashpoint highlighted. Flashpoint is the lowest temperature at which liquid gives off vapors that will mix with the air and be able to ignite. So flashpoint is the lowest temperature at which a liquid gives off vapors that will mix with the air and be able to ignite. So it's like gas, right? They said gas, it's not the liquid itself that's flammable, it's the vapors of gas. So gas can put off vapors at room temperature, right? If I had a pail of gas in the middle of the floor, vapors would be coming off of it, stuff like that, and they would be able to be lit on fire. Flashpoint determination. The whole first paragraph is highlighted for 2 highlights. The first one is the first sentence, I guess, and then the rest of the paragraph is a separate highlight. So really, they just want you to know the difference between flashpoint and fire point. So the first highlight in 310 is OSHA 1910-106A. We're on page 21 of the last chapter.
I caught the plane traffic on Vancouver.
What traffic?
Plane. They let out at 2, 3, or 4 o'clock.
But they have the
I
same
was-
thing.
Took me 30 minutes to get the bell chase from Jezebel. It's like cement or rock. Usually, if that.
I didn't realize, I guess we don't have plant traffic that y'all do with the West Bank.
We have like 4,400 people working there right now.
And which one?
The LNG plant they built.
There's 4,400 people working there now?
It's all the contractors.
Jeez.
Usually, if you try to leave in Bell Chase from 3 to 6 o'clock, it takes 30, 40 minutes to get out.
Are they in phase 2? Like, can you see building?
Oh yeah, they started construction, like everything, all underground is done, everything is going up now.
Like whenever you were done there last time, they were just finishing phase 1 or something like
We're
that?
transitioning from phase 1 to phase 2, we're still finishing up underground, running all wires and
For
everything,
like the parking lot lights or something like that?
all that's done.
When do they expect to run? They expect to run like,
We're gonna start producing, I wanna say, June or July next year.
that's nuts. It's nuts how fast they can build. I didn't even realize, y'all know the thing they built at the big structure that's right by the ferry, at PBF? Yeah. Like, I didn't realize that's been running for months. Yeah. Like I didn't, like the instrumentation guy was here a couple weeks ago. I was like, when's that gonna start running? He's like, it's been running.
So supposedly they have contracts with other countries.
Oh, I know the LNG plant has a contract for millions of tons of LNG with France.
That's what they already have ships over here. They're having to pay, keep these ships docked.
Oh my gosh.
That's what they losing crazy amounts of money right now. So they're gonna get part of the plant up and running to get some of the waters filled.
So they're behind
Oh, very.
in Louisiana.
There's rumors too that the main guy that started all this is like trying to get out right now. Yep.
It's too late.
I'm trying to sell all this, trying to sell and get out of it.
Because they're building way more stuff on the sides of it once they're done with
They're
the.
supposed to be building a whole nother one just like it right next to it.
All right, back to the highlight. I think I gave you a 310 first sentence. OSHA defines flash point as the lowest temperature at which a liquid gives off vapor within a test vessel in sufficient concentrations to form an ignitable mixture with air near the surface of the liquid. Mouthful. The rest of the paragraph is a separate highlight. A closely related and less common term associated with flash point is the term fire point. This is defined as the temperature at which the flame becomes self-sustained and continues burning the liquid. At the flash point, the flame does not need to be sustained. The fire point is usually a few degrees above the flash point. That's what you want to key in on. The fire point is a few degrees above the flash point. So flash point is just enough to ignite. Fire point is at the point where it can consistently burn wherever the concentration is. Flipping over to page 22, establishing the flash point, 311, flipping over to page 22. Second sentence on page 22 is highlighted. You can use the rapid flash test system to quickly determine if a flash point occurs below or above a specific temperature. However, it does not find the actual flash point temperature. The rapid flash test system does not find the actual flash point temperature. The immediate next sentence is an online test question. The auto ignition system works at extremely high temperatures. The auto ignition system works at extremely high temperatures. Online test question. This is why I don't understand. Mix these chapters up and it doesn't make sense to me. 320, measuring pH. You would have thought this would have been in the last section. pH instruments, 321. The whole first paragraph is highlighted. You're gonna have 3 questions coming out of the first paragraph. I keyed in on the last sentence, but the whole first paragraph of 3, 2, 1 is highlighted. As shown in figure 23, the numbering system for a pH scale ranges from 0 to 14. A value of 7 in the center of this span indicates a neutral solution. The values below 7 represent acid levels, with the smaller numbers indicating the highest acid levels. The numbers above 7 represent the base scale, with the larger numbers indicating the highest base levels. So 7 is neutral, 0 to 6 is acidic, and 7 to 14 or 8 to 14 is basic. And remember, like I said earlier, the numbers are not linear, they're logarithmic. So they're like acid with a pH of 5 is 10 times as acidic as an acid with a pH of 6. pH probes, 322. Last 2 sentences, the first paragraph is highlighted. Other systems use 2 physically separate probes called the pH electrode and the reference electrode, respectively. In either case, the actual technology involved is much the same. The next paragraph is highlighted going into the next page. The pH electrode is often viewed as a battery whose voltage varies with the pH level solution. This component is sensitive to hydrogen through the end of the paragraph and is often referred to as the measuring half cell. A special glass tube or membrane material allows hydrogen ions to pass into the tube. When the pH electrode is placed in the solution, a voltage proportional to the hydrogen ion concentration develops between the inner electrode and the outer electrode or the glass bulb material. Key in on the hydrogen ion concentration. 323, calibration and compensation. First 2 sentences are highlighted. Due to the way they work, pH electrodes require regular calibration. This is accomplished using a buffer solution. This is accomplished using a buffer solution. So it's just a, like I have, let me just go grab it. So pretty much when you're calibrating something, you need to have a known, especially with pH, you have to have a known solution. So this is the pH probe that we're going to use probably next class to just do our little lab. And taking the cover off that, you can see there's little probes on the bottom. That's what, like, these have separate probes, but it's all in one unit. But the buffer solution, like all these come with like a pH buffer solution. So it's like a little pack of powder in here. I mix this with a certain amount of water, and it gives me a perfect pH. This one gives me a pH of 7. This one gives me a pH of 4, and this one gives me a pH of 10. So I've got a neutral, an acidic, and a base that I can calibrate my pH probe to. These are like, you can create a buffer solution is just a solution of with a known pH that you can calibrate to. Page 26, 330.
That's pretty. I charted from here, but it's this is that's weird.
Might have to have an amperage charger for that phone.
That's weird. Never happened that. Never happened that to me.
Measuring conductivity. 330, the first paragraph is highlighted. A pH measurement system is designed to be sensitive to just one ion, the hydrogen ion. Similar systems can be designed to measure other specific ions There are applications, however, where it is necessary to determine the total concentration of all ions. This can be accomplished by measuring the solution's conductivity. Last paragraph, no. The paragraph that's right above that, G equals 1 divided by R. The first sentence is highlighted. Conductivity is sometimes referred to as specific conductance and is defined as a reciprocal of resistance in ohms of 1 centimeter cubed of the solution at a specific temperature. (332) Additional factors in measuring conductivity. First sentence is highlighted. Temperature strongly influences a solution's conductivity. Temperature strongly influences a solution's conductivity. Page 27, 340. Measuring oxidation reduction potential. The first paragraph is highlighted. Two questions coming out of the first paragraph. One of them is keying in on the first sentence, with the whole paragraph is highlighted. Oxidation is the loss of electrons by an atom, molecule, or ion with reduction of, while reduction is the acquisition of electrons. Every liquid has both oxidizing and reducing ions, but their balance varies from liquid to liquid. Those with extra electrons are called reducing agents, while those that have a shortage are called oxidizing agents. Next paragraph, first sentence is highlighted. The oxidation reduction potential, ORP, of a process liquid indicates by its voltage polarity. Key in on that voltage polarity, whether the process liquid has an oxidizing potential or a reducing potential. ORP instruments, so oxidation reduction potential instruments. Flipping over to page 28, that last sentence of that first started paragraph is highlighted. A port is provided for replenishing the potassium chloride, and a rubber sleeve protects the port from contamination. Port is provided for replenishing potassium chloride, and a rubber sleeve protects the port from contamination. That's all I've got for that section. You got 5 questions on page 30. right, let's run through these. Number one, temperature at which a liquid will start to form vapors that can ignite is the flash point, C. 2, if the liquid has a pH of 4.5, it is,
Neutral.
what's, it's an acid. Neutral is 7. Below 7 is acidic, above 7 is basic. 7 is neutral. Number 3, which of the following is used to calibrate a pH electrode or probe? B, buffer solution. Number 4, the environmental factor that can influence a conductivity measurement is
See.
temperature. And 5, if a substance has a shortage of electrons, it can act as a B, oxidizing agent. 5 is D. Section 4, gas analysis. Total hydrocarbon content, only trade term. 410, measuring oxygen. First sentence is highlighted. The demand for oxygen or O2 analysis is due in part to the essential role that oxygen plays in the combustion, oxidation, and other industrial process applications. Oxygen is used everywhere in industrial applications. 411, high temperature electrochemical sensors. Second paragraph, you're gonna have 2 questions come out of the first 2 sentences, keying in on the end of the first sentence. One type of high temperature electrochemical sensor commonly used in combustion control applications to determine combustion efficiency is the zirconium oxide oxygen sensor. This sensor consists of a cell made of ceramic zirconium oxide combined with the oxide of either iridium or calcium. I'm pretty sure that is an O2 sensor. Like an O2 sensor for like your car, like an O2 sensor in your car sees, looks at your exhaust and sees how much fuel is still in it or how much oxygen is in it. And then it can trim out your engine to run in a different manner based on that. But pretty sure that's talking about an O2 sensor. Which are, I know O2 sensors, just like in cars, they used them at the steel mill quite a bit to determine if there was a level of fuel. They had to make sure like all the fuel was evacuated from different chambers before they opened them up or something like that. So they used O2 sensors in order to do that. Page 32, still in the high temperature electrochemical sensors section. Second paragraph, the first full paragraph on page 32. Right in the middle, I've got an online test question. One disadvantage is that the zirconium oxide cell has a relatively short life, typically less than 18 months. One disadvantage is that the zirconium oxide cell has a relatively short life, typically less than 18 months. Well, that's not an O2 sensor then. It's like an O2 sensor because obviously O2 sensors last longer than several months. 412, paramagnetic analyzers, sentence before the bullet points is highlighted. Paramagnetic types of oxygen analyzers are the most commonly used in the following applications. And I've got the fourth one highlighted, medical applications. Page 33, 413. Galvanic sensors, first sentence is highlighted in 413. The galvanic oxygen sensor, also called the colorimetric oxygen sensor, is a chemical cell whose oxidation reduction potential, ORP, is changed by the introduction of the sample gas. 420, measuring carbon monoxide. The first paragraph, last sentence has 4 questions that come out of it. well, I guess it's the last sentence in the bottom left of the page. One such byproduct of combustible gas is carbon monoxide, CO, which is a colorless, tasteless, and odorless gas that combines with hemoglobin of human blood and inhibits its oxygen carrying capacity. You have 4 questions that come out of that one sentence. Why carbon monoxide is a big deal? Like a lot of times they're requiring carbon monoxide detectors in houses and stuff now, especially where you have natural gas appliances, because as you burn natural gas can also put off carbon monoxide. It can be odorless, tasteless. You're not gonna smell it. You're just gonna die. So that, like, whenever you turn on, and y'all have gas appliances, you just turn on the stove, but it doesn't light. You smell that smell. That's not what natural gas smells like. I guess carbon monoxide is also odorless, but natural gas, that egg smell is injected into natural gas so that you do smell it, so that you know something's wrong and turn something off or something like that. Actually, you notice whenever you're coming into the parish, like from the 9th ward, that big field that's on the right as you're coming into the parish, that's where they inject that like bad egg smell into natural gas, so that you know that your house is filled up with natural gas if you ever leave a burner or a burner on that's not lit or something like that. 430, measuring carbon dioxide. The first 1, 2, 3 sentences are highlighted. Carbon dioxide is a non-flammable, colorless, odorless gas, somewhat heavier than air. Carbon dioxide is one of the gases that make up the Earth's atmosphere, along with nitrogen, oxygen, and argon. It's a greenhouse gas, along with methane, water vapor, and many other gases. Out to the side of that, I wrote, oxygen is not a greenhouse gas. Oxygen is not a greenhouse gas. Anybody ever worked in a plant before?
They use like a,
What's that?
I see like the guys, they use yellow, it's yellow, they throw like
A monitor?
Yeah.
Yeah, that's what I was gonna say. A lot of times when you work in a plant, they'll have, you're required, it always annoyed me because it was kind of bulky and it just kind of hung off my shirt. But they have a 4-gas monitor that whenever, like, it measured oxygen, carbon monoxide, carbon dioxide, and something else. But if it ever like alarmed, then you knew you need to get away from wherever you were. And the important thing is like you guys are kind of training to be maintenance people. You're gonna be climbing in pits and going where a lot of people don't normally go. And like this just said, carbon dioxide is heavier than oxygen. So where you're standing on normal ground, everything's fine. You climb down in the pit, that carbon dioxide might have settled down in that pit. And you don't have crawling around on your knees or working on something nasty. You might not have oxygen when you think you do because that carbon dioxide. And there's a lot of other stuff. There's a lot of other gases that are heavier than air, and they would go down into pits and stuff like that. Like that's a big thing. Usually those are considered a confined space. And I know the procedures I had to follow where we had to have a confined space entry permit, and literally you had somebody sitting there with like a monitor with a tube down in the pit or something like that, and their only job was to sit there and make sure that you had, whoever was down in there had good oxygen flow and stuff like that. Page 34. Actually, wait, the sentence that splits the pages is highlighted from 33 to 34. Carbon dioxide is non-reactive or inert with many materials and is commonly used for applications such as blanketing and purging of tanks and reactors, and as a shielding gas in arc welding applications. So you can use carbon dioxide as a shielding gas in arc welding applications. That's the sentence that starts on page 33 and goes into 34. So carbon dioxide is non-reactive with many materials and is commonly used for applications such as blanketing and purging, tanks and reactors, and as a shielding gas in arc welding applications. The last sentence of that paragraph is also highlighted. At extremely low temperatures, carbon dioxide solidifies into dry ice, which is often used to freeze and preserve foods. The dry ice is just the solid form of CO2. It's pretty, like, it's kind of weird when you think about water doesn't act the same as everything else. Like, I guess that's not water, but like that carbon dioxide, like having solid carbon dioxide in that room temperature, it doesn't go to a liquid. It goes straight to a gas. If I had a big chunk of dry ice up here, it would just be fuming. But if I pressurize it, then it can turn into a liquid. So you can have, like usually if you ever see like liquid dry ice, it's in a pressurized tank that they can pour out and it immediately turns into like a big cloud temperature. 440, measuring hydrogen sulfide. The whole first paragraph except the last sentence is highlighted. Hydrogen sulfide, H2S, is a colorless, very flammable gas. In low concentrations, it smells like rotten eggs. It is heavier than air and very toxic. After just a few minutes of exposure at 100 parts per million, people lose their sense of smell and can no longer detect the presence or absence of the gas. So again, heavier than air. So that's another one that can sit down in tanks and stuff like that. At the top right of the page, that first full sentence up there, anabolic decay aided by bacteria such as occurs in sewers produces hydrogen sulfide. So that's why you never want like a sewer line in your house opened up in the house. Not only is it going to stink, that hydrogen sulfide is going to get in your house and it's not good for you. So anytime you're ever like pulling a toilet or pull a sink out, shove a rag in there, or shove a rag in the drain pipe or whatever till you're ready to close it back up, because that is sewer gas is not good for you. 441. Personal protection indicators. Second paragraph, first sentence is highlighted. One very simple device is a wearable personal protection indicator that changes color when exposed to toxic gases, including hydrogen sulfide. So that's kind of like I was talking about, except that's kind of a little bit cheaper version. Like you can have, a lot of times I've seen people put them on like their badge. So if your badge changes color or something like that, like it's indicative that you have come into contact with some type of gas or something like that. All the way on page 35, 450. Measuring total hydrocarbons. The first two sentences are highlighted. Hydrocarbons, compounds composed of hydrogen and carbon, are present in many forms in atmospheric air. Among these substances, methane, or CH4, has a concentration of approximately 1.7 parts per million, which accounts for the majority of concentration of hydrocarbons. .451, flame ionization detector, first sentence is highlighted. The instrument most often used to measure vapors for total hydrocarbon content uses the principle of flame ionization detection, FID. The next two sentences are a separate highlight. For this type of detector, the air sample and the fuel, hydrogen, are sent to the burner nozzle at the controlled flow rate. The concentration of hydrocarbons is determined by ionizing the hydrocarbons in the flame and then measuring the generated ion current, as shown in Figure 4. You got 6 questions on page 36. See if you can knock those out right quick. Let's go through these. Number one, the gas that is essential to combustion. Oxygen, B. 2, the best analyzer for assessing oxygen in the medical application is a C, paramagnetic oxygen analyzer. 3, carbon monoxide is a byproduct of combustible gas. Excuse me. 4, carbon dioxide is sometimes used in welding because it is non-reactive. 5, which gas ceases to be noticed by people in just a few minutes? Hydrogen sulfide, B. And 6, the most common hydrocarbon is methane. All right. Last section with me. Number 5 is B, hydrogen sulfide. Section 5, other analysis techniques. 510, measuring particulates. The first sentence is an online test question. Clean rooms are specially built enclosed areas that are specifically designed to control airborne particulates. Key in on airborne particulates. Temperature, humidity, airflow patterns, air motion, and lighting. Section 511, second paragraph. Got like the second half of the paragraph highlighted. I think it's just the last sentence is just long. For example, one method specified in Federal Standard 209E for counting and sizing the concentration of particles 5 micrometers and larger in clean rooms is to collect the particles on a membrane filter and then look through an optical microscope to count them. It's the last sentence of the second paragraph of 511. So you can see like the carbon particulates and their sizes. They can actually count those particulates in an optical microscope. Page 38. Discrete particle counters, DPCs. Third paragraph, last sentence. 2 types of DPC instruments are the optical particle counter, OPC, and the condensation particle counter, CPC. That's third paragraph, last sentence of 512. 2 types of DPC instruments are the optical particle counter, OPC, and the condensation particle, CPC. That's third paragraph of 512, last sentence. Paragraph that's right above 520 on the right-hand side of the page. First sentence is highlighted. The condensation particle counter, CPC, operates by saturating the heated sample particles with butanol, which is evaporated into the airstream, and then cooling the sample in the condenser. That's the first sentence of the last paragraph, the paragraph right above 520. Condensation particle counter, CPC, operates by saturating heated sample particles with butanol, which is evaporated into the airstream, and then cooling the sample in the condenser. Determining chemical composition. 521, gas chromatography, page 39. All the way at the top of page 39, that first sentence on the page, first full sentence on the page is highlighted. Chromatography works on the principle that when a test mixture is processed through the analyzer, the different components that form this sampled mixture separate and exit the chromatography process at different rates. The next sentence is also highlighted. This separation allows the individual components in the sampled mixture as well as their concentrations to be identified. You're going to have 3 questions come out of those 2 sentences. Skip a paragraph. In the last paragraph in the bottom left, the first 2 sentences are highlighted. The chromatography process involves 2 phases, mobile and stationary. In the mobile phase, the sample mixture to be analyzed is first vaporized and combined with a moving stream of carrier gas, such as helium, for subsequent passage through the chromatography column. The first sentence, the paragraph in the bottom left. Right-hand side of the page, second paragraph on the right-hand side of the page, first two sentences are highlighted. In some gas chromatographs, packed columns have been replaced by capillary columns. A capillary column is basically a very long tube, which generally has very small inside diameter. Page 40. Measuring infrared radiation. 531 basic theory on page 40. The first two sentences are highlighted. The second sentence is an online test question. Thermography is the technique of using optical and electronic system to convert invisible infrared radiation into visible light. This next sentence is an online test question. Thermography is based on the principle that any object having a temperature above absolute zero will emit some infrared radiation. Anybody remember what absolute zero is in Fahrenheit? It's like negative 460 degrees Fahrenheit. So that's why they use infrared technology quite a bit, because it's very, very, very hard to get to negative 460 degrees Fahrenheit to not be seen. 532, factors affecting infrared imaging. The sentence before the bullet points is highlighted. Objects can appear to be cooler or warmer than they actually are because of the following factors. And then I just have the first bullet point highlighted, emissivity of the object. Which if you flip back to emissivity is the only trade term, which is the ratio of the quantity of electromagnetic radiation that an object emits to the amount of theoretical perfect emitter would emit under the same conditions. .533 sensing equipment. That sentence before that last bullet point on page 41 is highlighted. The following are examples of infrared thermal inspection applications. And then if you flip over to page 42, I've got motors, transformers, and bearings all highlighted. So you can look at. It's not the face. Well, he has a face shield on because of the arc flash rating. But see his thermal camera. So he's looking at like breakers and switches. You can actually see, like if you look at a breaker panel, you can actually take a camera like this, which these are about $4,000, and you can look at a breaker panel and you can see, like if you have an issue somewhere in your house, you can see like hot breakers and stuff like that that might be because the more amperage you have, the more current you have, the hotter that's going to get. So you can actually see issues in a panel using something like this. You can also, like we highlighted, one of my jobs at Goodyear was to, like as an intern, was to walk around, and I had a camera like this, and I would take it and look at all the motors for the air compressors. We had big 1,000 horsepower motors that were twice as big as this desk. And the biggest problem with the motors was the bearings going out. So once a week, I would go take a picture of the bearings and see what the temperature was, and we could actually see, like as the bearings were going out week by week, the temperature would kind of rise as that would go, and it was just indicative of we need to, before this has a catastrophic failure, we need to pull this apart, replace the bearings, and put it back together. Transformers, you can have hot spots on a transformer. So you remember, like the transformer is essentially two coils of wire close together, right? Well, if those coils of wire ended up having like shorts in the middle of the coils, that can create hot spots. So you can look at hot spots with these types of cameras, and then just like I talked about, hot spots and wear for bearings. 534. infrared spectrometry. The whole first paragraph and first sentence of the second paragraph are highlighted. Another use of infrared detectors is in the science of spectrometry. Spectrometry is used to determine the chemical composition of an object. If an unknown sample is analyzed using a spectroscope, the chemical makeup of the sample can be determined. In absorption spectrometry, radiations of a particular wavelength in the appropriate region of the electromagnetic spectrum are employed. 540. Last, I can't believe I opened up every one of these. Last section, measuring ultraviolet radiation, UV analysis 541. I've got the whole second paragraph highlighted. It splits the pages. The UV absorption pattern of a compound is not so distinctive a fingerprint as its infrared counterpart, and fewer compounds absorb in the ultraviolet region than in the infrared. However, several important classes of compounds absorb strongly in the ultraviolet region, whereas water and the usual components of air do not absorb in that region. You want to key on that last half of the sentence. Whereas water and the usual components of air do not absorb in this region. As a result, ultraviolet absorption analyzers may be more selective and sensitive than infrared and other types of analyzers. So if you look at the light spectrum that's up on the board, this on the right, like this is the whole light spectrum in frequency, right? All that we can see with our eyes is right here. This is visible light, which is very, very minute side of all of this. So visible light, like this is the colors of the rainbow. So you have purple or ultraviolet all the way to red. So as you go ultraviolet, like we can't see ultraviolet and we can't see infrared, right? So that's why they're talking about using these two different things with different pieces of equipment in order to see this stuff. But just know that like you go further, higher up in frequency, you've got the ultraviolet rays, X-rays, gamma rays, cosmic rays, and then down here, you got infrared light, radar, television, FM radio. All this is like you can't see all of this. Like this is the only part of the whole graph that we can see. But they're just talking about using other frequencies of radiation other than what we can see in visible light. Advantages, 543, first sentence is highlighted in 543 at the bottom right of page 43. Compared to infrared analyzers, UV analyzers are generally more sensitive, yet they provide a comparable level of selectivity. Page 44. Flame detectors, last highlight I have for you. Page 44, it's the second to last sentence on the page. So top right, second to last sentence on the page. Ultraviolet detectors are considered to be superior to infrared detectors in this area because they are not affected by radiation emitted from hot surfaces inside the furnace. I will say I got pretty good at working on burner systems at the steel mill and stuff like that, and ultraviolet detectors were awesome. One of the tips, little small tip I had if you ever mess with a burner system is usually that's hooked up to some type of PLC, and it would go into like a DC input card because it's only going to see whether the pilot light or the flame is on or off. If you have an issue with one of these, you can pull out the scanner, and while somebody's sitting there looking at the PLC to see if that card can see the on or off, take a lighter and you just light it in front. And if it can't see it, then the component is bad. If it can see it, then something's probably wrong with the gas valve. Burners are, in my opinion, are super easy to mess with. But that's just like a trick that I learned that worked pretty much every time in narrowing down what components from. All right, that's the last chapter. I'm gonna go get the practice test. I know a couple of y'all need to take my notes from the beginning of the chapter, but we do not have class on Tuesday because of the trick or trunk here. There's gonna be 2,000 people here. We will have class next Thursday. Next Thursday, have all of the practice test and all of the book work done. You come in, I'll check it, you'll take your test, and then we'll be in lab the rest of the day. All right? Give me a minute to go get that test, and then you're free to go. Let me shut this recording off.
Change your book.